Hi, welcome to Making Game Productions Tools with Bifrost. My name is Maxime Jean-Mougin. I've been working at Platinum Games for the last 3 years as a technical artist, mostly focusing on dynamics and procedures modeling workflows. In today's talk, I will show you how we are using Bifrost to implement productions tools by going to two use cases: a hair simulation solver, which we use for cutscenes, and a procedural building generation toolset implemented as a collection of compounds. Before I got into Bifrost, my story with visual programming started with ICE. ICE was a user-friendly visual programming framework which was deeply integrated inside Softimage. Back in the days, it revolutionized the industry by making it easy for artists and technical directors to implement efficient tools simply by connecting nodes together. Thanks to its context-associated data, it made it really easy to operate on geometries and build all kinds of effects. After Softimage end of license, I switched to Fabric Engine. So Fabric was a standalone engine which was based around the KL language. User would write KL code or use Canvas, which was Fabric's visual programming framework, in order to build fast multi-threaded tools and applications. Fabric was integrated into all major DCCs and also Unreal Engine. It was also shipped with extra tools like, for example, Kraken, which was a popular cross-DCC rigging framework. And now we have Bifrost. So similar to Fabric, Bifrost is also a standalone engine which compiles graph to fast machine code. The graph has a lot of smart features like, for example, compound overload, meaning that the content of a compound can be changed depending on the input data type. You also have autoport types, which works a bit like templates in C++. It has various port-specific options, like, for example, port states, which allows you to update a value or an array inside a loop compound. You also have feedback ports, which are commonly used in simulation solvers to get the data from the previous iterations. Another smart feature of the graph is auto loop, which automatically turns a node or a group of nodes into a loop when you feed it an array. Bifrost in general is really flexible while still being user-friendly. In my opinion, it has the best of both worlds between ICE and Fabric Engine. So let's start our first topic, which is about our hair simulation solver. So our solver is a DFTL strand simulation solver, which we use for game cutscenes. We simulate strands, but we apply the result onto joint chains. We use Maya and Bifrost to have a better controllability over the simulations. Since we bake the result onto joints, we can simulate at a higher resolution and get a better result than when using the standard joint chain dynamics from our in-house engine. The dynamic solver is implemented using a dynamic follow the leader method to simulate inextensible hair. It works almost like a traditional position-based dynamic solver, except that it introduces a velocity correction term. While not being as physically plausible as traditional PDB, it's still perfectly viable for our use case. So at Platinum Games, we animate characters using motion builders, which means that in Maya, we only get the skeleton and the character geometry. We generate a rig to allow artists to control the shape of the hair. And then at each frame, we construct strands from the rig's controller and simulate them. These strands are then resampled to generate matrices which we feed back to the original joints. We have a script and a UI to simplify the setup of characters. Users simply select the joints that has to be simulated, and they can optionally add colliders too. Once the setup is done, our script generates all the rig object and the Bifrost nodes. Regarding the Bifrost node, we just generate multiple hair system nodes and a single hair solver node, which is where the simulation happens. So to construct our Bifrost graph, we use the VNN Python commands. VNN commands allows you to do any operation in a Bifrost graph. For each graph, we create the compound that we need, create the input and output ports, and do all the connections. Here you can disable and re-enable the graph resolver before doing these operations in order to speed up the process. There's a command called VNN bracket for this. It will speed up the process and make all the VNN operations almost instantly. In addition to the dynamic parts, we also use a rigging solver to make it easy to control the rest shape of our hair. This solver interpolates two driver chains and apply a local rotation offset to the constraints. This is a command solver used in rigging, nothing fancy here. So how we do that in Bifrost? So the solver takes both the constraint chains and the constraint chains as a 2D array. Each constraint chain has an interpolation fraction applied to it, and we use it to interpolate between the corresponding driver rotations. If a constraint misses a corresponding driver, we simply interpolate between 0 and the other driver. Since we're dealing with local rotations here, it doesn't create any problem down the line. So here's John from Bayonetta 2, which is the test model that was used during the development of this tool. Here we demonstrate how we typically set up characters. For each hair group that is needed, the artist simply select the chain stop joints and add them to the list. Once the hair group has been defined, the setup script generates a rig object and the dynamic solver, and then we're ready to simulate. And here is simple work animations with the default settings. So let's talk about the hair system graph. The hair system graph has two functions. First, generate the strands from the rigs controller and initialize the simulation's parameters, which we store as pure point geoproperties on our strands. So let's look at how we construct the strands starting from the rigs controllers. First, we generate the plane strands, which we only use to compute the length ratios. Then we generate a smooth cat-Milram spline, which passes through all the original points. We then resample this spline so that the points are evenly distributed along the curve. And finally, we generate the basis vectors, which are needed for the local shape preservation constraints. Once we have this, we can pass our strands to the simulation solver, which we'll talk about next. So let's now look at the hair solver graph. So this graph is where all the simulation related operation happens. In addition to the solver itself, we also initialize our colliders and also convert our gravity and wind controllers to vector forces. We then pass all of these data to the simulate hair compounds, which you see in the middle here. The simulate hair node is where all the simulation is processed. So our solver uses the same simulation standard as in all other built-in solver in Bifrost. We store all of the data into a single solver object, which is then passed into a compound using a feedback port in order to get the data at the previous frame. Then at each frame, we apply the simulation routine, starting by updating the previous and last positions, applying the forces, integrating, solving the constraints, updating the velocities, etc. Speaking about forces, we also implemented a custom wind force into our hair solver. Also, our solver can take Bifrost field influences. We needed something that worked nicely on low polygon characters. Our custom winds take the scene's controller's orientation and generate oscillations to the strands based on the length ratios, the point GDCs, and the various wind related parameters. And here's an example showing the custom wind in action. So I'm not going to go through all the nodes here, but I just wanted to talk about how we process the constraints. Since the FTL's constraints are inherently sequential, we can compute everything concurrently. So what we do here is process each strand in parallel and then process each substrand sequentially. Another thing that we implemented here is motion neutralization. This was definitely needed because we do a lot of action cutscenes. So we opted for the velocity shock propagation method, which was introduced by AMD and is currently implemented inside their trace effect simulation solver, which you can find on GitHub. It's open source. We could have implemented a trivial motion neutralization based on matrices, but we found that VSP to be a very attractive solution because it does not rely on external matrices. VSP automatically enables itself when a strand moves or rotates faster than a given acceleration threshold. So here's the same walk animation from before, except I applied a large offset on the x-axis. Naturally, the strands inherit the fast change of motion, so a very strong force is applied on the hair. And with VSP on, we can blend how much of that force we want to retain on our simulation. Okay, so once we have our strand simulated, we still need to apply the result on our joint chains. So to do that, we use the original length ratios to sample the strands in order to get the final joint positions. To generate the joint orientations, we apply parallel transport using the y-axis of the first controller of each chains. Finally, we convert our matrices from world space to local space and connect them to the original joints. And here's an example showing both the world and local matrices. Okay, let's start our second and last topic, where I'll introduce you to PGB, or Procedural Building Generator. So PGB is an artist-friendly procedural building generation toolset implemented as the collection of compounds. It was heavily inspired by Akira Saito's work, which I highly recommend you to watch. You can check his TEDx talk from 2019 called Mass Predictions of Procedural Buildings. And why do we use Bifrost? So nowadays, when it comes to procedural stuff, Houdini is most likely the most popular DCC application out there. However, our artist at Platinum Games uses Maya to do all the modeling tasks. So naturally, they wanted to have procedural tools directly inside Maya, and Bifrost was the perfect candidate for this. So here we have a very basic example where we use meshes directly from Maya and apply PGB rules onto them. We edit the input meshes to show that our system remains fully procedural upon edits. So PGB is based around face tags. Face tags are string labels which are stored on each faces of the mesh. All PGB operators takes one or multiple face tags as input to determine on which face to operate. Because our system does not rely on indices, our upstream topological changes will never break downstream operations. So here's the process used in all of our PGB modifiers. We start by searching which faces to process by comparing the face tags. The targeted faces are then extracted from the mesh and are processed in parallel. The modifier will generate new faces, which will also carry their own face tags. Finally, we merge the remaining faces with the newly generated faces. So PGB compounds are flexible enough to allow artists to use either daisy chain or branching workflows. Each compound outputs the global mesh, but also outputs individual ports for each newly generated groups. The user can use these individual ports to separate a chain into multiple branches, which can be processed in parallel. And we can merge these branches anytime using a dedicated merge compound. And here's a very simple example where we generate a building using daisy chain operations. The color you see represent the actual face tags. So we have a growing collection of compounds. I'm not going to go through all of them, but I'll show you the most interesting ones. All these nodes have terminal flags so that the user can enable them to see the result at each specific step. They also have a dedicated diagnostic flag in order to display some special debugging utilities. So first, the divider nodes. The divider nodes are the most commonly used nodes in the PGB collections. These nodes divide faces and generate new faces in different groups. The user can control the divisions by using two length parameters. The divider will then calculate how many faces can be generated inside the source faces. And for technical reasons, the length of the group A is always fixed. And we adapt the length of the group B depending on the available space. Users also have access to various modes to control the repetition pattern, like AB, AB, or either A or B at each boundaries. Depending on the need, some modes are more suitable than others. They can also define the direction of the divisions, either horizontally or vertically. The direction depends on the world orientation of the face. If the user wants to have a division horizontally, the compound will determine which edges has to be used for the division. To do that, we search for the lowest half edge vector and simply pick the next vertex indices as a reference. The divider compound is almost the same as what was showcased in Akira Saito's talk. We thought the concept was really clever, so our implementation has the same features. Again, if you want to know more about it, I highly recommend you to watch his talk. It's really interesting. Random tag. So this node simply takes face tags as input and apply new tags to a random selection of them. This node only has a single amount parameters in order to control how much of the original faces we want to overwrite. This can be used to apply a randomized variation to the building or even assign different materials to some faces. The instancer is a very important node because we can't add all the needed details procedurally. With this node, the user are able to apply handmade assets onto our procedurally generated building. The assets are stretched so that they fit into the original faces. We can also preserve the face tags of the source geometries, which is typically used to keep track of the material IDs. The extrude compounds works almost like the Maya extrude node. The main difference is that it targets face tags, like all other PGB compounds. It has some extra features like transformation and smart UVs. Smart UVs are very useful to maintain continuity between the original surface and the extruded faces. So the scatter node is a very basic compound. It's a variation of a Bifrost built-in scatter compound. It only has some extra features like border offset and overlap avoidance. This is typically used to generate assets randomly on the roofs or walls. So the pipe compound is a work in progress tools which generates pipes procedurally. We don't use it in production at the moment because it has some flaws, but we wanted to show it here anyway. Finally, we have the random shape compounds, which is used to create random building shapes. So this node selects a random point on a grid, performs a random walk, and grow the selection. We then generate a strands on the selection's outline, filter the low frequency corners, and reduce the point count to the strict minimum. Finally, we triangulate the strands using an air clipping triangulation algorithm, and we have our mesh. And here's an example where we apply simple PGB operations to different random shapes. So we're not done with PGB. There are still many features that we'd like to add, like Boolean operations or edge-based workflows. We would also like to evaluate how we could leverage Bifrost USD to generate our buildings. And finally, we'll investigate if we can integrate Bifrost directly inside our in-house game engine in the future. It could be really useful to generate assets directly at runtime. Okay, so I wanted to take this opportunity to say that we are hiring. We have a position in all our departments at both our Osaka and Tokyo studios. So if you'd like to work at Platinum Games, feel free to have a look at the recruitment pages there. Here's my contacts if you'd like to get in touch with me. If you have questions regarding this presentation, feel free to drop me a PM on Twitter. I'll make sure to answer all of them. I also have a blog where I occasionally write some Bifrost related articles, so feel free to have a look at it too. I'd also like to say that we have a Discord community dedicated to Bifrost. We have over 600 members now and it keeps growing. So if you're new to Bifrost and are looking for help, or if you just want to show off your work, feel free to join us there. And that's it for this presentation. I would like to thank Platinum Games for their support during the preparation of this presentation, and also a huge thanks to Autodesk for sponsoring the talk. Thank you for watching.